Okay, so as mentioned in the email this video is attached to, a passenger weighing 598 newtons rides in an elevator. What is the apparent weight of the passenger in each of the following situations? In each case, the magnitude of the elevator's acceleration is 0.5 meters per second squared. Now, part A is the passenger is on the first floor and has pushed the button for the 15th floor. The elevator is beginning to move upward. Part B is the elevator is slowing down as it nears the 15th floor. Now, I've drawn a force body diagram for each case for the passenger, and on the left is the force body diagram for the elevator with upward acceleration. On the right is the elevator with downward acceleration. The apparent weight is going to be equal to the magnitude of the normal force exerted by the floor on the passenger, and the only other force acting is gravity. Now, I was able to use Newton's second law to find the normal force from the weight and the acceleration that was given. So again, what we know is that the weight is equal to 598 newtons, and the magnitude of acceleration is 0.5 meters per second squared, and we're looking for the apparent weight of the passenger. Now for part A, I let the positive y-axis be upward. When the elevator starts up from the first floor, it has acceleration in the upward direction as its speed increases. And since the elevator's acceleration is upward, the acceleration in the y direction has to be greater than 0. And we kind of expect the apparent weight to be equal to the normal force and to be greater than the true weight. So the floor must push up with a force greater than W to cause an upward acceleration, obviously, which would make the elevator move. And then going by Newton's second law, which states the sum of the forces in the y direction is equal to the normal force minus the weight is equal to the mass times acceleration in the y direction. Well, since W is equal to mg, we can substitute m and get our formula. M is equal to W divided by g. And then we find that the apparent weight is equal to normal force, which is equal to the weight plus the mass times acceleration in the y direction, is equal to the weight plus the weight divided by gravity times the acceleration in the y direction is equal to the weight times 1 plus the acceleration in the y direction divided by g. And once I plug in all my values for that, I'm able to get that it is 629 newtons. And then when the elevator approaches the 15th floor, we're moving on to part B now. When the elevator approaches the 15th floor, it's going to be slowing down while still moving upward, though. So its acceleration is going to be downward, which means that the acceleration in the y direction is going to be less than 0. Now the apparent weight is less than the true weight because it is slowing down once it gets up there. So again, the formula is the sum of the forces in the y direction is equal to the normal force minus W minus it, which is equal to the mass times acceleration in the y direction. Except for this time, the acceleration in the y direction is going to be negative 0.5 meters per second squared. And the same formula is going to be applied here. Which is N is equal to W times 1 plus the acceleration in the y direction divided by gravity. And we plugged that formula in with our previous one to get the apparent weight is equal to 598 newtons times 1 plus negative 0.5 meters per second squared divided by 9.8 meters per second squared is equal to 567 newtons when the elevator is slowing once it gets to the 15th floor.